All right. Hello, everybody, and welcome to the virtual seminar series on Gaussian processes, spatiotemporal modeling, and decision-making systems. I'm so excited to have everyone here. Thank you all for joining us. My name's Alex Turenin. I'm a postdoc at the University of Cambridge and one of the organizers who will be hosting today's event. I'd like to thank my fellow co-organizers, Jeff Pleiss, Lisa Simonova, and Zi Wang for their work in helping to put the series together. And before we begin, I'd just like to make a few organizational announcements. First of all, following this keynote, we've got an amazing lineup of speakers for the coming weeks. And you can find the schedule on our website, which is gp-seminar-series.github.io. And I'll put a link in the chat. Here you can see the schedule for the upcoming seminars, so check it out. You can join seminars via Zoom, provided you register to receive emails with the links, which can be done on the website, or you can join via YouTube, which doesn't require any registration. Seminars take place at 1600 UTC, and that's Coordinated Universal Time, to be specific. And note that your local time may change due to daylight savings, so be on the lookout for that. If you're joining us via Zoom, you can use Zoom's raise your hand option to ask questions or type them in the chat. The speaker can choose to pause and answer questions during the talk or hold questions until the end, depending on their preferences. And with that said, it is my great pleasure to introduce Tamara Broderick, Associate Professor at MIT, who will give today's inaugural keynote on fast discovery of pairwise interactions in high dimensions using Gaussian processes. Tamara, the floor is yours.
Great, thank you. Okay, let me see if I can get this share here. Hopefully you can all see that. Super, well, it is fantastic to be here. Thank you so much for the invitation. Happy Pi Day to everybody. I'm excited to be chatting on Pi Day. Just to follow up on Alex's announcement, I am super happy to take questions live or to take them from the chat. I will just say that due to my setup, it's easier for me to see your questions if you ask them at the high level and not just privately to me. So if you're looking at the chat. Okay, so today I want to talk about how we often want to find a sparse, interpretable set of covariates associated with some response. But interactions between covariates can make this a much harder problem. And so today we'll talk about a fast and accurate solution. And I want to highlight the work of some amazing students from my group. Raj Agrawal is the first author on the paper or papers, depending on how you look at it, that I'll be talking about today. And his amazing co-authors are Jonathan Huggins, who's now a professor at Boston University, and Brian Tripp, who will be graduating from my group very shortly with his PhD. Okay, so let's first start by talking about a little bit of a cartoon. So suppose I have a bunch of data on gene expression levels. I can imagine this is pretty high dimensional data. In my cartoon, maybe it doesn't look super high dimensional, but in real life, it might be pretty high dimensional. And I have this for capital N different individuals. And maybe I also have some environmental information about these individuals, like how much are they smoking, how much are they drinking, how much are they eating their vegetables. And I'm pretty interested in some health response, like what level of blood pressure do these individuals have? Now, if I'm going to be doing some follow-up science here, or I want some kind of health indicator, then I probably care which genes or environmental factors are associated with this health outcome, like blood pressure. Now, because this can be so very, very, very high dimensional, P, let's say, is our number of covariates here, and we're imagining that P is greater than N, is greater than N, as is often the case in biology and sometimes health, that we probably want a really small subset of those covariates for interpretability, to be able to do follow-up science, et cetera. Now, we have a great tool for this, the lasso. But the lasso has some limitations. So for instance, in its vanilla form, it's this additive model. We're sort of saying, once we know the association of any particular gene expression level or environmental factor with blood pressure, that's the end of the story. But we think that in many cases, we really want to learn interactions too. Like it seems very plausible that if I have some gene, then smoking and blood pressure have some association that's different if I don't have that gene. And so I'd like to be able to pick up those kinds of interactions. Now, the problem that we essentially face at this point was we already had this super high dimensional problem of size p, both statistically and computationally. And now we have this sort of impossible problem of size p squared. And so that's what we're going to be addressing today is how can we discover things like pairwise interactions in high dimensions. It'll turn out we can actually get beyond pairwise, but I'm going to focus on pairwise in the talk today. Okay, so the punchline is we're going to see that we can provide a fast and accurate Bayesian method. So that's where the Gaussian processes are going to come in. It's basically going to be hinging on a Gaussian process model for interaction discovery. We'll see that it provides better scaling in P, and better accuracy than lasso-based methods, and it's just orders of magnitude faster than naive Bayesian inference. Okay, so in the remainder of the talk, I'm first going to say a little bit more in terms of setup, like notation and so on, for discovering these main and interaction effects. I'll talk about our method, which because it's Bayesian has a Bayesian generative model. We need to do fast inference. So this will be the part where it becomes really important that we're using Gaussian processes, and we need to use fast report or have fast reporting of results. Again, it will be really important at this point that we're using Gaussian processes. And we'll see some experiments on both simulated and real data to see the efficacy of this method. Okay, let's start with the setup, the notation and so on for discovering these main and interaction effects. Okay, so let's add a little bit of notation to our cartoon from earlier. So here we have our covariates, let's call them x1 through xp. So there are p total covariates, and we remember that we're thinking of p as being quite large. We have some response in our cartoon, it was blood pressure, let's call that y. We're going to collect our covariates together with the with a 1 into a vector, let's call it x. And the most straightforward thing we could do here is a linear model. We could say, hey, our linear model encapsulates that we're interested in something like the association of our various covariates with our response y. So here the superscript n denotes the particular nth data point. And then theta at a particular element, like theta sub k, will tell us the association of that covariate, the corresponding covariate with y. And you can see why we have this 1 now in the covariates, that it's letting us have an offset in theta. Okay, so now we said we cared about interactions, this idea that maybe actually I could have some gene expression levels interact with environmental factors or between gene expression levels or so on. And so a straightforward way to handle that is to just expand our covariate space. Let's not just have x1 through xp. Let's have x1 times x2, x2 times x3, x3 times x4, and so on. And so let's collect this in an expanded covariate space that we're going to call phi2 of x. And the 2 is denoting that we're including these interactions, these pairwise interactions. Okay, so now we can just take our original linear model and expand the covariate space. Implicitly, by doing this, now theta is a roughly p squared size vector. I'm going to say p squared. I mean, obviously, there's like a constant in here and some little offsets, but like it's roughly on the order of p squared. And so each one of its corresponding elements will tell us the association now of not just the main effects, but the pairwise components as well with our response y. Okay, so in some sense, we're done. I mean, that's the model. What we want to do is we want to, 1, do parameter selection. We want to find this small, sparse subset of non-negligible thetas, and we'd like to know the values of those thetas, so that's parameter estimation. Now, in just saying that, I've made some assumptions, and so I'd like to make those assumptions explicit. The first assumption is that we have sparsity. And in particular, we're going to look at 2 types of sparsity assumptions for the purposes of this talk today, and then I'll talk about getting a little bit beyond them at the end of the talk. But the first one is sparsity. So we're going to assume that most main effects are negligible. And so again, we need this for things like interpretability or follow-up science. We're certainly not going to look at all of the p different gene expression levels or environmental factors in general. Our second assumption is essentially sparsity on the interaction effects. We're going to assume this very common assumption, strong hierarchy, that I have an interaction only if the main effects are present. So only if I have some non-negligible relationship between gene A and blood pressure, and I have some non-negligible relationship between gene B and blood pressure, can I have a non-negligible relationship between the GA times gene B interaction and blood pressure? Now, that isn't always going to be appropriate, but it's going to be an assumption that we make today, although we'll see exactly where it comes up, and that'll give a hint as to how we can get beyond it in the future. Okay, yes, and we'll see this in the discussion briefly. Okay, so what's the problem? You know, this is a straightforward linear model. I mean, this isn't nearly as complex as a lot of the stuff we see nowadays. Well, the problem is that it's so high dimensional, that we have these p squared covariates. P was already too large. P squared is just way, way, way too large. And so this yields both a statistical and a computational challenge. And so just at a very high level, we're going to get into this more very shortly. The way that we get around this is that these aren't just any p covariates, or any p squared covariates. If we truly had as our covariates x1, x2, x3 up to x p squared minus 1, x p squared is a p squared cost. You can't do anything. But these really are p squared covariates that fundamentally depend on x1 through xp. And so we're going to use that structure together with the sparsity assumptions we've just made to reduce to a problem that's fundamentally linear in p rather than quadratic. Okay, so we have the goal, we have the overall likelihood model. Now let's talk about filling in our Bayesian generative model, getting inference and getting reporting of results. Okay, so we're going to take a Bayesian approach. Why Bayesian? Well, there are a lot of nice things about the Bayesian framework that are relevant here. We want to be able to incorporate expert information and prior information that we have to deal with uncertainty quantification, to use regularization, to deal with the high dimensionality, and use the flexibility of the graphical modeling framework. Okay, so what are the parts of doing Bayesian inference? Well, the first thing we have to do is we have to choose a generative model. The second thing we have to do is we have to approximate or compute our posterior in some way. And the third thing we have to do is report relevant summaries of the posterior. Usually we don't report the whole posterior, we just report some summaries. Okay, so let's first look at number one. We do introduce a new Bayesian generative model for our purposes here. We call it the sparse kernel interaction model, and basically it imports sparsity and strong hierarchy. I'm not going to focus on it so much today, though, because we really stand on the shoulders of giants here. We're really using ideas from existing papers, like this beautiful paper by Carballo et al. 2009 and Piranen and Vitari 2017 that show how to have sparsity in Bayesian modeling. Also, there's been these fantastic papers about potential ways to handle interactions in Bayesian modeling. So Chipman 1996 and Griffin and Brown 2017. We do have technically a new model, but I think it has a lot of similarities to these models. We think that the important part where we come in is in steps 2 and 3, making this something that you can really compute on. These last papers sometimes struggled with even dozens of covariates, and so we really want to get into much higher numbers of covariates. Okay, so the first thing we're going to need to do is compute the posterior. Why is this challenging? Well, remember, we have p squared on the order of p squared parameters. And so on the face of it, it seems like any step in something like MCMC would have to visit every one of those parameters, and that would take p squared time. And so we're going to see that we can develop a kernel interaction sampler that actually runs in p time per iteration rather than p squared, again, using this special structure. Okay, now we're going to have to report relevant summaries of the posterior. In particular, we want to say, what are the non-negligible main and interaction effects? Well, on the face of it, again, this seems hard because there are p squared parameters. And so to tell you whether one of them is non-negligible, it seems like I have to go to each one of them in turn, and that would take p squared time. And so again, we're going to see that we can use this kernel trick to report all the non-negligible main and interaction effects in p time rather than p squared. Okay. So let's dig into this a little bit deeper. Let's start by thinking about, what would be the default here? What's a nice baseline for what we could do? Oh, and I'll just mention before I go on, these aren't just for SCIM. We use SCIM, our model in all of our experiments, but actually parts 2 and 3 could work for other models as well. Okay, so let's start with the default. What's the default thing we could do here? Well, we have this parameter theta. The promise of modern probabilistic programming languages is that I should be able to just put my model in, have it get sampled and get these fantastic samples and go. And so why would that be problematic in this particular case? Well, we have these p squared parameters. And so on the face of it, just computing the likelihood in a default kind of way is you're going to have to visit every one of these parameters for every one of your data points, and that's going to take time p squared at. And in fact, we see this borne out. Okay, so I haven't told you our method yet, but I'm going to start comparing it to these defaults. And so in particular here, on the horizontal axis, we created a bunch of simulated problems with dimension p. On the vertical axis, we have running time of either our method in green or option 1, as I'm calling it, sort of default using probabilistic programming languages in red. And you can see, in fact, that we get this much worse scaling with option 1. Now, something that if you are familiar with MCMC, you may well be asking yourself is, well, did they mix? Maybe one of these mixed better than the other. Well, in fact, what we're doing is 1,000 iterations of MCMC in the Stan language. R hat is a nice way to get a sense of heuristic about did you mix. And in fact, option 1, we find that R hat is greater than 1.05 for all the parameters. And so there's evidence that it seems like, in fact, this was not mixing. And for our method, R hat was less than 1.05. So if anything, the story is probably worse than what we're seeing in this plot right now, that this was just the timing comparison for 1,000 iterations, but actually our method seems to be mixing, whereas this alternative method does not seem to be mixing. Okay, so that seems like it's not working out. We can't just use sort of default probabilistic programming languages. Is there something else we could do? Well, remember the model that I just showed you a moment ago is just a linear model. In fact, we have conditional conjugacy. The immediate prior next to the linear model is a conjugate prior. Now it's got some of its own hyperparameters, and so we don't have full conjugacy, but we have some conditional conjugacy. And the word on the street is that if I use conditional conjugacy, then all my problems go away and everything's perfect. And so let's try that out. Okay, so now let's use conditional conjugacy for theta. Now, if you have ever done any kind of conjugate Bayesian linear regression, which if you are used to using Gaussian processes, you probably have in one form or another, then you know that we have to do something like compute and invert X transpose X, where that's our covariate matrix, plus some kind of prior precision matrix. Okay, for the purposes of computation, let's just ignore the prior precision matrix and focus on X transpose X. Again, just for computation, this is roughly the same. Okay, well now in our case, we don't have X as our covariate matrix. We actually have phi2 of X. So recall that X is n by p size, and phi2 of X is n by p squared size. And so what do we have to do to compute and invert this matrix? Well, first we take our n by p squared matrix and we pre-multiply it by a p squared by n matrix. This whole thing, in the end, when we do the multiplication, is going to be p squared by p squared matrix. And any one of its entries, we're going to have to do this n by n dot product. That's going to take time n to compute. Okay, so computing this whole thing is going to take on the order of p to the 4th n computations, and inverting it is between quadratic and cubic, but I'm just going to say p to the 6th. Anyway, it's all really bad. We said p squared was too much. This is now like way, way, way too much. Okay, you can use some like fancy linear algebra, like the Woodbury matrix identity, and you can get it down to p squared n squared. But remember, we said like p squared n was too much, so p squared n squared is still definitely too much. And we see this borne out in practice. So here, again, on the horizontal axis, we're creating a bunch of simulated problems. We're increasing dimension, again, on a logarithmically increasing or an exponentially increasing scale. On the vertical axis, we have running time for the naive method, for using the Woodbury matrix identity, and for our method, which I still haven't told you what it is yet, but we can still make these comparisons. And we see that we're getting, again, these sort of orders of magnitude speedups. And it's not just running time, it's also memory. This is also an issue in terms of memory. Okay, so we can't just do straightforward conditional conjugacy for theta. We can't just compute and invert phi2x transpose phi2x. What are we going to do? Okay, well, hopefully, as this is a Gaussian process crowd, you're somewhat familiar with this problem. You recall from the way that we typically think about Gaussian processes that, hey, Gaussian processes can be thought of as some kind of conjugate linear regression. It's just that we actually have often an infinity of covariates. And so there's no way we would ever do this computation and inversion. And so how do Gaussian processes get around this problem? Where they don't, the way that Gaussian processes get around this problem is we don't ever try to get the posterior on theta directly. Instead, we use conditional conjugacy for theta transpose phi2. So let's review why it's better from the perspective of Gaussian processes, to get conditional conjugacy essentially for the predictor rather than theta on its own. And then we're going to have to come back and notice that in this particular problem, unlike Gaussian process regression, we actually do care about theta. So we'll have to get that somehow. But for the moment, let's just see if we can get around this problem by looking at conditional conjugacy for theta transpose phi 2. Okay, so that's the approach. Spoiler that we're going to learn here, that we're going to use here. That was the thing that I proposed, or that I showed you in the previous graphs that we compared to. But again, let's see why it would be so much better. Well, on the face of it, it's not any better at all. I mean, when we think about, what is our posterior covariance going to look like? It looks like it's worse. Like we pre and post multiplied by phi 2x. So it seems like we have to do the same calculation we did before, but with some extra calculations. And the key observation we're going to make is that actually, if we just compute this thing that I'm now highlighting in green, and that's much, much, much faster, and then multiply it with the same thing, which is the remainder of that product, and that's much, much, much faster. We don't ever have to actually do that one inner dot product, or that one inner matrix multiplication, I should say. Okay, let's convince ourselves this is true. What does it take to compute this thing? Well, now we're taking an n by p squared matrix and post multiplying it by p squared by n matrix. So the thing we get out is an n by n matrix. So if p is much greater than n, and p squared is greater than p, which is in turn greater than n, this is going to be way, way, way smaller, even more than my cartoon is letting on. And so certainly when we multiply that by itself, we're only going to have n costs. We're not going to have any like p squared costs. So we're already seeing where this might benefit us. Now, our remaining problem is, what does it take to compute any entry of this matrix? Well, on the face of it, it looks like we have to do this p squared by p squared dot product. And that would be bad because we would still have p squared costs. But this is where the kernel trick comes in. This is where we're going to use the fact that we have these very special structured covariates that are x1, x2, x3, x1 times x2, x2 times x3, et cetera. We really have a polynomial kernel here. And so we only have to sort of sum up over the x1, x2, x3, x4 components and then multiply them. And so in fact, this is just going to have a p cost rather than a p squared cost. Okay, so as a result, because we have this kernel trick, we can have the construction of this matrix is n squared p, multiplication of an n by n matrix by an n by n matrix is just going to be, it's just going to involve n's, it's not going to involve p at all. And then an inversion of this n by n matrix will be somewhere between n squared and n cubed. And so if what you care about is p being greater than n and p squared being way, way, way greater than n, this is great. If you're still concerned very reasonably about n, you're definitely going to have to deal with that at some point. That is still a concern. But from the perspective of this very high dimensional case, this was the big thing that we needed to deal with. Okay, so this is what we compared to in those previous plots. This is how we got the big speed ups relative to just naive usage of probabilistic programming, which, by the way, I should say is like fantastic. I think, keeping people's user time down, having the ability to do these things automated is great. It's just that in some cases like this, we have to be a little careful. Okay, so now that we have something that runs in a reasonable amount of time, that has this good, behavior and time cost, we can compare it to these lasso-based methods, and that's what we're going to do going forward. Now, before we do that, will the same trick work if you consider phi 3 with polynomials of order 3? Absolutely. Okay, so I phrased this as we were all doing pairwise interactions. In fact, you can do k-wise interactions for whatever k order that you want. And so certainly three-way interactions, this will work just fine for as well. I will say that we tended to focus in our paper in terms of experiments on pairwise interactions because I think those were easier to describe and it was clear when people really cared about them. I'll say it at the end again, but if now or later you in your life really care about either three-way or higher interactions or pairwise, I would love to chat just about applications. Okay, so let's go on. Now, before we see comparisons to Lasso, though, there's still one problem that we haven't dealt with, and that's reporting. So we haven't totally worked this out yet. In particular, at this point, we said that we can access the posterior of essentially this Gaussian process in time p per iteration. But we are not yet at the point where we can actually report our posterior over theta, which is what we really cared about and what we really wanted to report. One more question. If n is small, so there's a speed up, should we be worried about the statistical implications of searching over p-squared terms? So my hope is that I've convinced you in doing this, and maybe I'll do so even more by going through this next part, that we've sort of reduced this to essentially a p-sized problem, even statistically. So I think that's why we're seeing that really poor mixing in the default usage when I talked about just using stan for the theta, is precisely because we're doing like this searching over a p-squared space, and that's humongous. Here we, in some sense, we've reduced it to like this p-sized problem that like the parameters that were or sort of a representation of this problem is a p-sized problem. But we still have to make sure that that's true in reporting as well. And so that's what I'll address on this slide. Okay, so remember, our goal is to find the main interaction effects, which in fact is p-squared size. So we're looking at sort of like this p-sized representation in what's effectively our sampler, but in the way that we just did this conditional conjugacy. And so now we want to see, can we actually find these main and interaction effects? Okay, so first, I'm going to convince you, hopefully, that we can report the posterior of any main effect, let's call it theta sub xi, so that'll be the theta associated with xi, or interaction effect, let's call it theta sub xi xj for the theta associated with xi xj in linear time, or sorry, in constant time. That's not enough because there's still p-squared of them, but then I'll get to that next. Okay, so in order to convince you this is true, let's look at EI, the ith basis vector. So it's got a 1 in the ith position. Now, if I'm interested in G of EI, that's going to give me theta xi plus theta xi squared, because all the other theta terms are going to have a 0 multiplied by them. And then the only theta corresponding to an interaction term that's going to be non-zero is going to be when I get a 1 from the xi term and a 1 from the other xi term. Similarly, I can do G of negative EI, this basis vector, and I'm going to get a negative 1 in front of theta xi, and I'm going to get a negative 1 squared, or 1, in front of theta xi squared. Now, I can add these together. For instance, if I want to recover theta xi, or sorry, I can subtract one from the other and divide by 2 if I want to recover theta xi. If I wanted to get theta xi squared, then I can add them together and I could get that out. And because everything's Gaussian, because we're dealing with Gaussian processes, we know that we're going to get a nice Gaussian out and be able to characterize its distribution. Okay, so this tells me, because I have this nice Gaussian process representation, in fact, I can recover my posteriors for all of my thetas. And not only that, but I can do it in constant time. Now, the problem is, how do I actually report everything in p time rather than p-squared? Well, what we're going to do is take advantage of our sparsity assumptions. So the first sparsity assumption is that actually not every main effect is active, only k much less than p. So k is just the number that is representing the number of non-negligible main effects here. I'm not assuming it's a constant, I'm just giving it a name. So that's going to take OP time to go to every one of the main effects, theta 1, theta 2, theta 3, and ask, is it non-negligible? We find the non-negligible ones, and then because of strong hierarchy, we only have to look at those in the posterior when we're reporting. So we're not assuming this in the model itself. This is purely a reporting thing here. We're just saying, what do we even have to look at in the reporting at the end of the day? And because we have these sparsity assumptions, it's just going to take p time to go through those. Okay, so now we have this fast way to do posterior inference. We have this fast way to do the reporting. And so finally, we can go and do our experiments and compare to these lasso-based methods. Okay, first, we should check timing. So my experience is that often when I talk to people who are applying these ideas and applications, they're like, yeah, Bayesian methods sound cool, but my lasso method is super fast, and so I'm going to use that. And so we have to have something that's going to be competitive with lasso methods to even compare accuracy. Okay, so what are we going to compare to in terms of lasso methods? So first, we're going to compare to what we're going to call pairs lasso. What we mean by pairs lasso is just that expanded covariate space with the lasso regularizer. So we have the x1 times x2, x2 times x3, et cetera. There's also this really cool idea, hierarchical lasso, which was specifically set up by Lim and Hasty in 2015 to deal with this pairwise interactions problem that I described. Now, both of these take time p-squared per iteration. On the face of it, that sounds really worse than what we talked about because our method takes time p per iteration, but maybe the devil's in the constant And we want to make sure that even for moderately sized problems before these meet, that like the timing isn't too far off. Okay, so let's look at what happens before they hit each other in terms of the p squared versus p. So again, here we're going to have increasing dimension of simulated problems on the horizontal axis. We're going to have running time on the vertical axis, as we saw before. Our method is in green. It is slower in the beginning than hierarchical lasso and pairs lasso, but we find that it quickly catches up to them for moderately sized problems. Okay, so we can run our problem, or we can run our method in a reasonable amount of time. Now let's talk about accuracy. Is it going to meet lasso in terms of accuracy? Okay, now there are two types of experiments that we have in our paper. Selection experiments, we compare these methods on selection, we compare them on estimation. I'm going to focus on selection for our discussion today, but you can check out our paper if you're interested in estimation. Now, for selection, this is a really tough problem. I mean, this is true for estimation as well, because we don't have ground truth. So we have to ask ourselves, how are we going to compare these methods when we don't have ground truth? What are the covariates that are truly associated with the response? And so what we're going to do to address this problem is we're going to start with simulated data where we do have ground truth because we made it up ourselves. And then we're going to recognize the problems with simulated data and slowly build our way up to real data. Okay, so first, we're going to just make 36 different simulated data sets. Why do we do this? Because we know the true effects. We created them ourselves, and so we can test on them. We're going to take P up to 500. That means in terms of actual total parameters, because remember, the total parameters is on the order of P squared, we have about 125,000 parameters. If you really treated this as a P squared size problem, this is a super challenging high dimensional problem. Okay, and as I said, we're going to focus on selection for the moment. Okay, one of the things that we're going to be looking at is false discovery rate. What's the proportion of incorrect effects that we're finding? Okay, now I'm going to show you a pretty busy plot, but I'm going to discuss everything that's going on, so bear with me. Okay, on the horizontal axis, we have the number of correct effects that a particular algorithm is finding. And so here we're saying, hey, we know that there's a real effect. How many of those real effects did it find? How many non-negligible data did it really find? On the vertical axis, we have the number of incorrect effects. So this is a case where we knew that there was truly a negligible, or in this case, 0 theta, but the algorithm picked it up and said, like, no, I think that this is really actually a non-negligible theta. Now, suppose you look in the upper right-hand corner at that little red plus. That is hierarchical lasso run on one of the 36 different simulated data sets. So there's a little plus for every data set. And we can see that this particular run of hierarchical lasso is picking up all 5 correct effects. So it turns out there were actually 5 correct effects. So that's great. It's doing really well at picking up correct effects. But it's picking up over 60 incorrect effects. So that's like an order of magnitude more incorrect effects, and that's undesirable. We actually want that to be as low as possible, ideally 0. So if we look at all the little red pluses, we see that there's this tendency for them to be picking up lots of correct effects, but tons of incorrect effects. And here we're looking specifically at main effects. Now, if we look at the little crosses, the little blue crosses, that's pairs lasso. We can see that they're not picking up too many incorrect effects. They're much, much lower on the vertical axis, but they're also much lower on the horizontal axis. They're not picking up many correct effects. Our method are the little green dots. They're picking up lots of correct effects, but also a lot fewer incorrect effects. Now we can see the same plot for pairwise effects. So here in pairwise effects, we see that hierarchical lasso, again, tends to be in this upper right corner. It's picking up lots of incorrect effects, lots of correct effects, but also lots of incorrect effects. Pairs lasso is picking up lots of correct effects, but also lots of incorrect effects. Our method is down lower. It's picking up lots of correct effects, but fewer incorrect effects. And in general, we can see that these false discovery rate lines, they're telling us as we get lower and lower false discovery rate, which is desirable, that our method is getting this lower false discovery rate, but importantly, it's also just getting a lot of correct effects. Okay, so very reasonably, you could be saying to yourself at this point, yeah, but simulated data doesn't always look like real data. So here is one thing that is unrealistic about this simulated data. As with many people who make simulated data, we made covariates and they were independent. Real life covariates are not independent. They're not remotely independent. So how could we get something that's more realistic, that gets at more realistic behavior of real life covariates? Well, here's an idea. Let's take some actual real life covariates and then just simulate the effects. So we'll say we know the real thetas and we'll simulate the y's in those thetas. So that's our next experiment. So we're just going to use real covariates, but we're going to simulate the effects. And again, we'll have 5 correct main effects and 10 correct interaction effects. So here we use this residential building data set. It's this publicly available data set. Like many real life data sets, it has highly correlated covariates. So 20 out of 105 of the covariates capture 99% of the variance. Here we're going to look at the number of correct effects, which again, we know because the effects themselves are simulated, and the number of incorrect effects, which again, we know because the effects themselves are simulated in this experiment. So here, we want the number of correct effects to be higher, and we want the number of incorrect effects to be lower. Okay, so first let's look at pairs lasso. So here, we're seeing that it's picking up 2 correct main effects and 5 incorrect main effects. It's picking up 3 correct pairwise effects and sort of an order of magnitude, unfortunately, more incorrect pairwise main effects. So that seems undesirable. We'd ideally like to pick up as many correct effects as possible and as few incorrect effects as possible. What about hierarchical lasso? Well, it's picking up 3 correct main effects. That's slightly more, but way more incorrect main effects, unfortunately. So 19 here. It's picking up sort of on the same number of pairwise effects. It's picking up 3 correct pairwise main effects, pairwise effects, and 18 incorrect pairwise effects. Our method in this case is able to pick up as many correct effects in all of these cases. You'll notice none of them are picking up all the correct effects, but we're picking up as many as these other methods, but 0 incorrect effects. And so that's desirable. That means, we come up and we do some follow-up science and we don't have to spend all that extra time following up on things that we knew didn't have an association to begin with. Okay, but again, you could reasonably have complaints. So here is a reasonable complaint you could have here is that we generated the data. And so real life isn't always this nice linear relationship. Maybe when I deal with real life data, these other methods will perform better because of the nature of what is the actual relationship between the response and the covariates. And so again, we have this awkward situation where we actually don't know ground truth when we have a real response and real covariates, because here we're trying to estimate these associations. And so what can we do? And so what we're going to do next is we're going to start with a real set of covariates and response, something that we have no notion of ground truth for. But what we're going to do is we're going to append a ton of fake covariates. And so while we don't know what's going on between the real covariates and response, we do know that nothing is going on between the response and the fake covariates because they're totally fake and they have nothing to do with the response. And so we'll try to get closer yet to real data that way. Okay. So here we're going to take, by design, a very low dimensional set of covariates, because most of our dimensionality is going to come from our fake covariates. So we use this auto miles per gallon data set. P is just 6 of real valued covariates, because again, the mass majority of our covariates here are going to be totally fake noise covariates. They have nothing to do with the true response. We don't know what's going on between the real covariates and the true response, but we definitely know that nothing is going on between these fake noise covariates and the true response. So that means, yes, we have 200 covariates, but because the fundamental problem is to get these main effects and interactions, we actually have something like a 21,300 parameter problem. That's a super challenging high dimensional problem, again, if we work in a p-squared space. Okay, so now you'll notice our key is a little bit different from last time. We do not know the correct effects. And so we can't say higher is better for correct effects because we simply do not know them. The most we can say is that, hey, what number of original effects did we pick up? It would be nice if the number was not 0, because if it were 0, there's nothing going on there, but we just don't know what the original effects are. What we do know is that the fake effects are fake. And so when we look at how many fake effects each algorithm picked up, lower is better there because we don't want to pick up any fake effects because we know they're all fake. Okay, so what happens here? So first, let's look at pairs lasso. It picks up 4 original effects. Again, very nice that that number is non-zero, but we don't really have any ordering on the blue anymore. It picks up 0 fake main effects. That's great. That is desirable. We don't want to pick up anything fake. It picks up 2 original pairwise effects. Again, we don't have any ordering on that number, but it's nice that it's non-zero. It picks up 78 fake pairwise effects. That's definitely fake. It's way, way, way bigger than the number of possible real effects that could exist here, and so that's undesirable. Hierarchical lasso picks up 6 original main effects. Again, there's no ordering relative to pairs lasso for the blue because we don't know what's real. Picks up 46 fake main effects. That's undesirable. That's a lot more than could possibly be real effects. It picks up 4 original pairwise effects. Again, there's no ordering on this, but it's nice that it's non-zero. And it picks up 38 fake pairwise effects. Again, way, way, way bigger than the number of possible original effects. Okay, so our method picks up 3 original effects for main effects, picks up 0 fake main effects, so that's great. We know that those were fake, and it's good that we didn't pick any up. Picks up 1 original pairwise effect and 0 fake pairwise effects. And so at least coming into this, I might think that maybe I can trust these 3 original effects and main effects and 1 original pairwise effects more, because it seems to not be, not be picking up the fake effects that we're seeing and that we know are fake elsewhere. Okay, so what we talked about today was the ability to get these fast and accurate detection of pairwise interactions. If you're interested in basically the main paper that I talked about today, you can check out our paper in ICML 2019, the kernel interaction trick, fast Bayesian discovery of pairwise interactions in high dimensions. Now, there was code with our original submission, but actually I think it's really awesome that these fantastic Pyro contributors who are totally not us and are just awesome people have added this to Pyro. And so if you're interested in trying it out, you can actually just try it out directly in Pyro, and I think that's wonderful. It makes it probably way easier to use, so that's fantastic. As was already mentioned earlier in our discussion, this is actually not specific to pairwise interactions. You can use the same kernel trick, the same Gaussian process trick with a polynomial kernel with higher order interactions. And again, if anybody is interested in that, like you truly care about higher order interactions, also if you truly care about pairwise interactions, I'd love to chat. Okay, what have we been doing since this? Well, one is to get beyond nonlinearity. So one thing you'll notice here is that we started from this linear model, but it's not always the case that we have associations that are purely linear between a set of covariates and a response. So we've been working on getting away from that in this new paper that is up on the archive that uses the same Gaussian process tricks, just with a sort of more complex functional ANOVA kind of flavor. So the SCIM FA kernel, so the FA stands for functional ANOVA. You may recall that we talked about SCIM as a model today. This is again the same thing, but with functional ANOVA for high dimensional variable selection and nonlinear interaction discovery in linear time. This paper also is able to remove the strong hierarchy assumption. So we talked about that today. As if you think about it, where did that even come up today? It came up in the reporting. And so if you were able to do something where in your model, you could really focus on, hey, what are the actual covariates that have something going on in the model in any form, either main or pairwise, then you could get away from that. And that's kind of the idea of what happens here. An elephant in the room that I don't think we have really yet solved, but is certainly worth solving, is improving the scaling in N. So Raj, again, the fantastic PhD student now graduated who has worked on this, has some thoughts, but I think that this is an open problem, as any of you who work in Gaussian processes, I think will be familiar. One thing I will mention is that we have done some work in scaling Gaussian processes. And so in this first AI Stats 2019 paper, we looked at focusing on scaling Gaussian processes with guarantees. So in particular, having guarantees on the quality of the finite data mean and variance estimates that you get by scaling. There's also this fantastic paper that we worked on data-dependent compression of random features for large-scale kernel approximation. But I want to suggest that the way that we were thinking about things, both in these papers, and I think the way that often people in the Gaussian processes community are thinking about things, is in terms of spatiotemporal modeling. where you're saying, oh, the thing that I can take advantage of is that I'm far away in time or space, then I'm going to be, uncorrelated, and that's how I speed things up. And here we have like the opposite problem because we're dealing with a polynomial kernel. And so we can't just slot in these ways of scaling things up that we or other people have worked on because we have this fundamentally different kind of kernel that we're focusing on in the Gaussian processes. So I think there's probably some cool work to be done there. Okay, and then finally, we're super interested in applications. We started talking with various biologists who I think are very interested in this kind of thing, but we're very open to talking further if anybody else is interested in this as well. And then finally, I'll just plug some work that is not directly related to the stuff I talked about today, but on the subject of Gaussian processes. So we have this AI Stats 2022 paper, so just about to appear in AI Stats just around the corner, on measuring the sensitivity of Gaussian processes to kernel choice. And so you can imagine, especially if you're doing spatiotemporal modeling or something like that with Gaussian processes, you make a kernel choice, but it's often out of convenience. It's not like the squared exponential is the only thing that could possibly reflect your prior assumption of stationarity or Materin kernel. And so what if you had a slightly different kernel that still respected that prior belief? Could you possibly change your analysis? We find some cases where you can, and some cases that are robust to kernel choice. So if you're interested in that, I'll check that out. I will say that the reason, again, this doesn't apply here is because we have this very special kernel setup in the paper that I talked about today. Our kernel isn't something that we choose as a modeling choice. It's because of this speed up that we're trying to get. And so it's sort of given to us by this setup of like trying to find sparsity. And so that's very different from using a Gaussian process as like a chosen model when you're trying to learn something perhaps in a spatiotemporal domain. Great, and that's it. Thank you so much for listening, for everybody who came out on Zoom. I see we already have some more questions, which is great. Thanks for the virtual claps. Really appreciate it. Yeah, if there are no objections, I'll just launch into questions. I see at least one now, but feel free to, if anybody has more.
So for purposes of the questions, I'm just going to sort of stop the YouTube live stream and things there. And after that, we will move on to the question and answering and the discussion period for this talk. And I just want to say again, before I do that, a thank you to all of the wonderful audience on YouTube that joined us, and check out the talk that's coming up